So in this video, we'll talk about net electric field, just like how there's net force. So remember in the net force problem, we had something that looked like this. So I'll have Q1 here. That's 1 times 10 to the negative 9 Coulomb. Q2, let's have at 2 times 10 to the negative 9 Coulomb. And then Q3 we'll have as negative 2 times 10 to the negative 9 Coulomb. And we'll put them all 1 meter apart. Okay, so if I wanted to find the electric field, right, and I'm just gonna, whatever, the electric field at Q1, right, I need to find the electric field that Q2 produces and the electric field that Q3 produces. So I'm gonna make this a little more clear, at Q1. Okay, so let's do the electric field at Q1, it's an at sign, at Q1 by Q2. Remember that the electric field, I'll put it up here, the electric field is K Q over R squared. So we have 9 times 10 to the 9 Newton meters squared per Coulomb squared times the charge, and we're talking about that Q2 produces, so we use Q2's charge. 2 times 10 to the negative 9 Coulomb divided by 1 meter squared, and that's going to give us 18 newtons per Coulomb. And if we want to find the electric field at Q1, that's produced by Q3, same thing, 9 times 10 to the 9 Newton meters squared per Coulomb squared times the charge of Q3, negative 2 times 10 to the negative 9 Coulomb divided by 2 meters squared. And that'll give us negative 4.5 newtons per Coulomb. And so again, it's important to think about this kind of convention of electric fields. The convention is to point the arrow in the direction that a positive charge would go if placed there. We actually do have a positive charge here at Q1, which is kind of convenient. But we know that the electric field that Q2 would produce would be going this way, right? Because if Q1 is placed near Q2, it'll be repelled. But the electric field produced by Q3 is attractive, so go this way. You see that these are going opposite directions, so we need to subtract these two numbers. And again, what I do is I make them both positive, and then I subtract. And we see that the electric field of Q1, which is making it repel, go to the left, is much stronger than that of Q3. So Q2's electric field is stronger than Q3 at that point. So what we do is then we just subtract. So we have 18 newtons per Coulomb, and subtract. Remember, I make both positive, 4.5 newtons per Coulomb, and that gives you 13.5 newtons per Coulomb. That's the net electric field. Which means, if I wanted to find the force on Q1, I just have to get Q1 and multiply it by that net electric field. And that's just going to give us 1 times 10 to the negative 9 Coulomb times 13.5 newtons per Coulomb. So that'll give us 1.35 times 10 to the negative 8 newtons of force. And that is net electric field. And again, make sure you practice it and think about it.